Okay, welcome back everybody. Today we're doing lesson 1.3, Rational and Irrational Numbers. Now just a quick definition of rational and irrational numbers, or maybe a practical definition, is that rational numbers can be written as a fraction of two numbers, and irrational numbers cannot be written as a fraction. But we'll get into this a little bit later. Let's look at example 1. Part A says here, convert 28 over 11 to a decimal. So 28 over 11 to a decimal comes out to 2.545454 and so on, or we can write it as 2.54 repeating. The decimal representing 28 over 11 has a repeating pattern and does not terminate. It does not terminate. So repeating and non-terminating. This would keep going on forever. 2.54545454 and so on. Okay. Example B, convert 28 over 8 to a decimal and we get 3.5. So this decimal is non-repeating and it terminates. Alright, let's look at the last example 1C. Convert the square root of 2 to a decimal, and that would give us 1.41421356 and so on and so forth until your calculator runs out of space. So this square root of 2, when converted to a decimal, is non-repeating. There's no pattern, repeating pattern, and it does not terminate. Okay, so let's quickly look at some of the definitions down here, some of the vocab, and we have our four possible scenarios. We have a repeating decimal, which means the decimals have a reoccurring pattern of the digits. A non-repeating decimal, decimals have no pattern, have no reoccurring pattern. Terminating decimals, decimals with a finite number of digits. Finite just means it stops somewhere, it doesn't keep going on forever. And then non-terminating, we're looking at infinite number of digits, so it would keep going on forever, such as in the case above here. Okay, so example number 2. State whether the decimal equivalent of each number is repeating or non-repeating, and also state whether it is terminating or non-terminating. Okay, let's look at example number 2A. So 1 over 8, or 1 divided by 8, is the equivalent of 0.125. I don't see a pattern there, so it is non-repeating. So I'm going to just put NR, non-repeating, and comma, it obviously stops, so it's terminating, and I'm going to put a T right here for terminating. Okay. 2 divided by 11 gives us 0.181818 and so on. So this one here is a repeating. So it is repeating, comma, non-terminating. It keeps going on forever in this pattern. Okay. Okay, C is a little bit tricky. 9 divided by 7 gives us 1.28571. 28571. And then that pattern actually repeats again. So 28571 keeps going on forever. It's repeating. So it is repeating and non-terminating. All repeating decimals are obviously non-terminating because they repeat on forever. Okay. D is already a decimal, so it's 0.9, and then the 4 repeats, so 0.94444. So D would be same as the previous one. It would be repeating and non-terminating. Okay. Okay, let's look at this square root of 8 over here. The square root of 8. When we get, it's not a perfect square, so we're going to get a decimal of 2.82827, and so on and so on. So this one is non-repeating, so we'll say NR, comma, non-terminating, NT, non-terminating. Okay, the square root of 0.16 actually gives us, the answer is 0.4, and this is clearly non-repeating, comma, terminating. It doesn't keep going on forever. Okay, so let's revisit our definitions again. So we're looking at rational numbers first. So rational numbers are decimal numbers which repeat or terminate and can be written into a fraction. So again, we're looking at terminating or repeating, and those can be written into fractions, and those are called rational numbers because they can be written as a ratio of two integers, such as 4 over 5 or 7 over 9, whatever the case is. On the other hand, if we have decimal numbers which are both non-repeating, okay, so there's no pattern, and non-terminating, meaning they go on forever, those cannot be converted into fractions, and they're called irrational numbers. Irrational numbers. I guess a good way to think about it, irrational, maybe a little bit crazy, because they keep going on forever and they have no pattern to them. They're all over the place. Like this one up here that we had, this one over here. Okay, that one would be irrational. Okay, moving on to example 3 on the next page. We have to identify whether the following numbers are rational or irrational, and then give a reason for each case. Well, the first one is a decimal, but it stops. Okay, it terminates. So it is a rational, and then I can put here it's a rational number, and then maybe a comma, and the reason would be because it terminates and it's non-repeating. So terminating and non-repeating. Okay, the square root of 5, if we punch that in our calculator, we're going to get 2.3606. It actually keeps going on forever with no pattern. So this one, this is the irrational one, so it's going to be irrational irrational, and I'm going to put the reason because it is non-terminating. Keeps going on forever, and there's no pattern, so non-repeating. Okay, let's look at the next one. 2.547547547. This one does seem to have a pattern, a repeating pattern, and it is 547, 547, 547. So 547 are the repeating digits. So this one would be a rational, and it's a rational because there's a pattern. So it is non-terminating, but it doesn't matter because it is repeating. It is repeating. Okay. All right, and we have the square root of 81, and then a negative in front of that. So the answer would be -9. I've memorized my square roots, and -9 is clearly a rational number because it can be written as a fraction, as 9/1. And we can just give one reason. We can just say that it's terminating, and that's good enough to satisfy the definition of rational. Okay, E, we'll take the square root of 4.41, and we get an answer of 2.1. So again, this is a rational number because it terminates. Let's look at the last one. -8.131133111333. I don't see a pattern here, even though at first glance it might look like there's a pattern. From what we have here, there's certainly no pattern. So this would be, to me, there would be non-repeating and non-terminating. So it would that would make it an irrational number because it is non-terminating, non-repeating. Okay. Example number 4. Order the following irrational numbers on the number line. Okay, how are we going to do this without a calculator? I think it wants us to estimate what these numbers will be and then order them on the number line. I think the best way to do this, because I certainly can do the square root of 14 in my head, but I know what square root of 16 is. The square root of 16 is 4. Is 4. Therefore, I know that the square root of 14 will be close to 4. So what I might do is I'll just say that it's maybe somewhere around, somewhere around here, 3 point something, maybe close to 4 there. Okay, pi. Pi, we all know that pi is 3.1415 and so on. So that's pretty close to 3 there. So 3.1, so it's just a little bit more than 3, so I will maybe put it over here. Let me mark these as A. This would be B. Okay, C, the square root of 80, we're going to use a similar method to A. I know the square root of 81. The square root of 81 is 9. Therefore, the square root of 80 is just going to be slightly less than 9. So I'll put it over here as C. Okay. D, we have 2 times the square root of 15. Well, the square root of 15, I'm not sure what it is without a calculator, but I know that the square root of 16, is equal to 4. So I'm just going to estimate here. I'm going to estimate that the square root of 15 is going to be very close to 4. So even closer than A. And then I'm going to have 2 times 4 because there's a 2 in front of here. And that would give me an answer close to 8. And what I actually should put is 2 squiggly lines like that, which means that it's not quite equal to 8, but it's very close to 8. So I'm going to mark it on my number line here. This is going to be D. Okay, the square root of 0.1, again, that's going to be, okay, sorry about that. The square root of 0.1 is going to be very close to 0, but not quite 0. So I'm going to put it somewhere just between 0 and 1, maybe closer to 0 over here. And that's going to be E. Okay? Alright. Okay, so the next thing we're going to look at is how to convert a repeating decimal to a fraction algebraically. Your calculator can't really help you here. If you have a repeating decimal, you need to be able to put it into a fraction using your algebra skills here. So without going through these steps here, which you can read later, I'm just going to show you how to do this with a few examples down here. So example A, we have 0.36 repeating, so 0.36363636, and so on. So what I'm going to do is I'm going to let x equal 0.36, which is my repeating number here. So I'm just going to, label my repeating number as x here. Okay. Then the next step, I look at my repeating part, and my repeating part is two decimals, two decimal places, 3 and 6, so tenths and the hundredths. So what I'm going to do is I'm going to multiply both sides of this equation in red by 100, and I'll tell you why 100 in a second. So if I multiply everything by 100, I'm going to get 100x equals, and then if I multiply the right side by 100, I'm going to get 36.36 repeating, because ultimately this is just 36, 36, and so on, and then the same thing here, 36, 36. It keeps going forever. So the reason I multiplied by 100 is because I wanted to get the repeating part, which is the 36 here, on the left side of the decimal, Okay, now your final step here is to subtract the red equation from the blue equation. So let me just rewrite the red equation here, and the red equation was x equals 0.3636 repeating, or 3636, and so on. So I'm going to put a big minus sign here and do some math here. And let me just do the left side first here. So if I have 100x minus 1x, I get, so I have 100 of something minus 1 of something, I get 99 of something, and that something is x in our case. And then I have 36 minus 36.363636 minus 0.363636, and what I end up getting here is 36, because this whole side over here cancels out, because if I just subtract one from the other, they're the exact same thing. I'm going to end up with 0, so it's going to be 36.0, but I don't need to write that point there. So now the final step, I want to get x by itself, so I'm going to divide both sides by 99, and that gets rid of my 99 here. So x equals 36 over 99, which simplifies to 4/11. Okay, and if you put that in your calculator, 4 divided by 11, you should get 0.363636, and so on. Okay, let me do another example. Okay, so we're looking at 8.25, and let me just mark this off over here. So I have 8.25, and notice that it's only the 5 that's getting repeated. So my first step, I want to get that 2 over to the left side of the decimal. But sorry, before I even do that, I'm just going to let x equal my original number, 8.25 repeating. Then the second step is I'm trying to get the 2 on this side of the decimal, on the left side of the decimal, and in order to do that, I need to multiply by 10. Both sides of the equation by 10. So when I do that, I end up with 10x on the left side and 82.5 repeating on the right side. I just need to start. I just need to have just the repeating part on the right side of the decimal. Okay, then I'm going to multiply everything by 10 again, and this time I'm going to get 100x equals 80 or 825.5 repeating. Okay, the key thing you're looking for here is to have just the repeating part on the right side of the decimal. Now I'm going to take the top one and subtract it from the bottom one. Let me rewrite it though. So 10x equals 82.5 repeated. And when I subtract that, I get, well, 100x minus 10x equals 90x, and then 825 minus 82 is 743, and the key thing is that my repeating part cancels out, because 5 repeated minus 5 repeated is 0. Last step, I'm going to divide both sides by 90, and that gets x by itself, and 743 divided by 90 simplifies to, actually I don't think it simplifies to anything, so your final answer is 743 divided by 90, and if we put that in our calculator, you will end up with 8.25 repeating. Okay, I'm going to do the last one fairly quickly. So first step, I need to get the decimal over here and get the repeating part, just the repeating part on the right side of the decimal, and everything else on the left side of the decimal. So in order to do that, I'm going to let first of all let x equal 4.072 repeating. Then I multiply it by 10, both sides by 10, to get 40.72 repeating. And now so I don't need this anymore. Okay, now I'm just working with the bottom one here, and my next step is to get the repeating part to the left side of the decimal. And in order to do that, I need to multiply it's 2 decimal places, so I need to multiply by 100. Okay, so if I multiply this by 100, I'm going to get 1000x, because 10 times 100 is 1000, equals 40 times 100 gives me 4000. Sorry, 4000. 4000. Let me just erase this. It's 4072.72 repeating. And what I've done here is, again, I've isolated my repeating part. So when I subtract equation 1 from equation 2, the repeating part is going to disappear. But let me rewrite equation number 1 down here. So 10x equals 40.72 repeating. And so that's again equation 1. So I'm just going to subtract those, and again 1000x minus 10x gives me 990x, and then 4072 minus 40 gives me 4032, and again the repeating part cancels out. Last step, divide both sides by 990 to get x by itself. And let me see if I can simplify this. 4032 divided by 990 simplifies to 224 divided by 55. Okay, that's all for now. See you guys next time. Thanks for watching.